Okay. So I think I gave permission to share already,
Gotcha.
but let me,
Try it out. Is that looks like it's working?
okay, let me just move this around. Okay. Mm, girl. Yeah, looks good. You're good to go.
Oh,
Oh,
yeah. So, hey y'all. I'm Professor Lillian Chin at UT Austin. I'm in the Electrical and Computer Engineering department. Happy to talk to y'all. There's a football game going on right now where UT's winning, but I'm putting it aside so I can talk to y'all. Um, so I'm here to talk about material matters, designing robot bodies in dialogue with computation. So normally when we think about futures of robotics, we think of movies like Star Wars and Star Trek. And in those, there's a lot of robots either helping with real-world tasks like message delivery or being in close contact with humans, sharing a tight cockpit. So how close are we to achieving these futures? I would actually say we're pretty close to the real-world tasks idea. Already, you can buy off-the-shelf robots that can carry things around your house, that can vacuum, and that can perform surveillance. But how close are we to this idea of sharing a tight enclosed space with robots? So I would argue we're actually pretty far from that. So a couple of years ago, there was this chess playing robot playing against a boy, and as he reached for a piece, the robot mistook his hand for a chess piece and broke his finger. Similarly, maybe you've seen these mall robots running around, but another case was that it ran over a toddler because its sensors could not see it in time. So if we're looking at this idea of robots sharing a closed space with humans, I think we're actually pretty far away from that. What's causing these issues? If you read the news articles about these stories, they're blaming the children. They say that the children should like not following safety rules or that the robots should have a sign that say go away, do not touch. And this is pretty common for industrial settings where robot arms are actually held behind cages because it's considered too dangerous for humans to come into close contact. But as robots become more and more popular, these safety rules are going to be followed even less. So this was earlier this year during the Spring Festival in China. And if you, oh, it is muted, but so if you watch this, right, like if you look at this with a programmer's eyes, there's clearly just something like some programming bug that happened with this. But for the popular idea, it looks like, oh, the robots are going to attack, maybe the robot shouldn't have been this close to the people in the first place, but this is going to be just more and more common of a problem as the technology develops. So, what is causing these issues? What I would argue is why we're seeing these cases of safety violations appearing is because we think of robots as a body carrying a brain. This is a concept from Cartesian dualism. So, you might have heard like Descartes' I think, therefore I am. And it's an idea that the body and the brain are separate things, that the body is just in service to the brain and carrying it around. We see this also in how we talk about machine learning. So one of the more common ideas is this idea of cross-embodiment transfer. The idea that you can have a single controller to work over across all quadrupeds, all robot arms, all mobile robots, right? This idea that the brain is kind of universal and can go across these different bodies. So there are very impressive results with this, but I kind of want to challenge this way of thinking. That instead of thinking about robots as just a body for a brain, what if we consider what a body can give us? What are the unique capabilities that being in a body gives? This is called embodied intelligence, and it's a new way of thinking about robots, especially from the mechanical engineering side. Some ways that you can think about it in our everyday life is when you're in the kitchen, right? So if you're chopping an onion very fast, you're relying on this rocking motion between you and your hand in a way that current robots can't achieve. Current robots are very thinking about like where should we put the knife at each step rather than using the body to kind of do this motion. The same thing applies to stir frying, right? I can't do this walk thing, but I have a sense that it's understanding how the vegetables are moving and using the wok as an extension of your own body. If we start thinking this way, we start thinking of the body not as a limitation, but of new capabilities that it can provide. So this is from a YouTube creator called Alexis, who runs Stump Kitchen. And she has a limb difference, but she's pointing out that, rather than thinking of it as a deficiency, who needs a juicer when you have a stump? She's using the unique properties of her own body to do new things in the kitchen. In fact, if you start looking at this way of looking how bodies can give this intelligence, you start seeing new things. For example, let's say the reflex. So you approach a candle, you feel that it's hot, and you jerk backwards. So in the Cartesian dualism model, you would expect that these sensors need to translate all the way to the brain. But actually in our own bodies, it goes to the spinal cord so that it can have a faster response. So we have the sensory neuron to tell when it's too hot next to the candle. It connects to a relay neuron through the spinal cord and then goes to your motor neuron to jerk backwards. So we see intelligence in the body, like embedded into the material itself. This is also, again, a new way that people are thinking of robots. So from this paper, we can see what the challenge is. Sensing, actuation, and computation are the basic principles of robotics. However, rather than using discrete components for achieving these functionalities, the major challenge is to fully embed them into the material itself. So instead of grabbing a sensor or a motor off the shelf and stitching them together, what if we have a single material, a single body that has all these functions in it? In fact, if you look at the science robotics grand challenges, this idea of coming up with new materials and new ways to make them are labeled number 1. So this question of how we can think of bodies and materials in robotics is the focus of my lab, the Merge lab. We study how materials embody robots geometrically. So the core focus of what I do is in sensors and actuators, right? Coming up with new ways to 3D print things and add touch sensing to structures, as well as new ways to make things move. So these fun geometries cause things to twist and extend and twist and expand. I use these as the foundation. So its core is sensors and actuators, but I'm drawing on a lot of different fundamentals in order to build up this research. On the one side is disability justice, so looking how people with disabilities shape the world around them to better fit their bodies, like adding in this pencil grip so that you can apply your makeup even if you have an abnormal hand. I also look into the mathematics, so looking into how people design geometries to then put them into robots. And then finally, I'm interested in applying the sensors and actuators that I make into medical devices and robot manipulation. So using these sensors to improve the control of an exoskeleton, as well as using the sensors and actuators to create better grippers that can feel the world around them. In this talk, I'm going to be really focusing on this reflex model, where you have motors, sensors, and structure. On the motor side, I'll be talking about these new kinds of geometry and how you can get different movement from them. On the sensory side, I'll be talking about how you can use 3D printing to embed tactile sensors into almost anything. And then finally, I'll be putting all of this together so to create new embodiment-aware robots. And this is some of the more cutting-edge stuff in my lab that's been coming out. All right, so I'm going to start with actuation, these motorized auxetics. So one way that I'm able to control the body and its different material properties is this thing called mechanical metamaterials. So what is that? Normally, when you think of materials, right, you kind of go to Home Depot and you buy some things off the shelf, right? Wood, copper, steel, aluminum. There's a lot of materials out there. So it's really nice because there's a lot out there, but the challenge is that you can't say, oh, I want wood, but a little softer, or I want copper, but a little less conductive, right? It's because it's dependent on the material's atomic properties. You've got these atoms working together, and the atomical properties then create the overall material properties. So what metamaterials says is, what if we go beyond that, right? Like meta beyond the normal material properties. And we get there by creating new unit cells out of these base materials. So by changing the geometry of it and tiling that individual unit cell, you now get a metamaterial with new properties. Here's an example of this. So normally, this is a 3D printed plastic, and if you print something out of PLA, you don't usually think of it as, having plier properties. But by having different kinds of geometries and tiling them together in different ways, we now get this kind of clamping process. So that's metamaterials, getting new mechanical properties from a base material. People have explored lots of different ways to use metamaterials in robotics. Category one is this beam bending model. So you can see how there's these different hourglass shapes that then create this bending motion in the actuator. Another example is doing folds and cuts. So in this one, they have this unique snake skin that causes the actuator inch forward like a worm. And then finally, you can think of putting fibers into different orientations. So in this system, based on how the structure is knit, we see that the flower unfolds and then curls upwards based on the fiber pattern. So there's a lot of different robots that are using these properties, but to me, I think there's two major drawbacks. One is that these structures tend to use metamaterials as a passive constraint. So there's some other actuation source that then causes it to follow the metamaterial structure, but the metamaterial is not an active part of the system. Also, because the metamaterial relies very heavily on what the geometry is, you can either optimize it for actuation or sensing, but not the two of them at once. And so both of these are things I'd like to address in my research. In particular, I use the beam bending model, and I'm going to talk about auxetics specifically. All right, that's a big word. What are auxetic materials? Normally, when you pull on a rubber band, it gets skinnier, but auxetic materials are interesting because when you pull on them, they get thicker. This property doesn't exist in nature. The closest thing we have is cork, which is why it's used to plug up wine bottles. But if you again take this geometric view of it, you can see this rotating square model. So the squares will rotate against each other, and you see that the overall structure is larger than what it was before. Here's the animation version if you're bad at visualizing, but you see these black and white squares rotating against each other and causing an overall expansion of the material size. We're not just limited to the 2D case, we can also do it in the 3D one. So if you know Buckminster Fuller from like Epcot or Buckyballs, he also made this fun little thing called a jitterbug. And in this jitterbug, you can also see the triangles rotating against each other to get this expansion. So I was very interested in this structure and really used it as the basis for new robotic actuators. From a mechanical engineering perspective, what's exciting about this is that with a single degree of freedom, right, this rotation, you can get expansion and a control over this overall movement. So we created this auxetic shell. So it doesn't look like it, but it's still got the same squares and triangles. And then we gradually increase the angle between the squares and triangles until it hits this point of maximum expansion. If we continue to increase the angle between the square and triangle, right, as denoted in orange, we see that it collapses back down. It reaches this point of maximum expansion and then goes back in to shrink down. So just by controlling the orange angle theta, we can control the overall expansion of the structure. And this is how we ended up creating auxbots. So here are the squares and triangles again, and they're made out of water jet aluminum pieces. We use a lead screw to force an expansion through the overall range of motion, and we also have these 3D printed dihedral angle constraints so that we can maintain a certain angle of rotation that they move through. Because we are so closely tied with the geometry, we see that our overall robot has very close matching to what is predicted by the mathematics. This is to our advantage because it means that geometry is on our side and we can create a very forceful robot. So to create this moving, forceful robot, we add this wire constraint between individual auxbots, right? So that rather than expanding linearly, like all at the same time, we now see this curvature start to appear right here. So here's how it looks when the robot is moving, right? We see this overall expansion, and then the constraint layer causes it to have this flipper motion that goes forwards. These robots are extremely strong. They're about 76 times, they can push outwards with 76 times their own weight. And also they can move 10 times faster than comparable modular robots because it's able to use this force to push against the ground and move itself forward. This force is so powerful that even if we're putting on a weight, so nearly 1.5 times its own weight, we can still move forward and keep this locomotion, even with some of the modules stall out, which shows sort of the exciting parts of modular locomotion, that individual modules can stall, but the overall system keeps moving. So this is just the most naive version that we can think of for applying the geometry, right? We took the jitterbug and directly made it into a robot, having these squares and triangles to rotate against each other. But what happens if we change the geometry a little bit? So we went from these force-focused version to the expansion-focused, and you can kind of see that it expands much larger and also much faster. So instead of 0.7 seconds, it moves in 0.2. We do sacrifice some blocked force as a result, but the expansion gives us ability to access more dynamic applications. To achieve this, we take the square and triangle and we sort of make two layers off of it, so rotating against each other. We do this so that in between each of the two layers, we can have a scissor link connecting them, so that the scissor link will add more expansion to it. Finally, since we're interested in making this softer and faster, we use we did laser cut spring steel, so which is a much more pliable thing, and direct servo drive. So rather than having the expansion being controlled, we're changing the angle theta directly. So this is what the much faster expansion ratio looks like, right? We're expanding much faster and at a much smaller time stamp, so we can just, have this dynamic motion. In fact, we have the fastest expansion speed of other modular soft robots since we don't have to wait for inflation for this thing to move. So if I've timed it right, we get this dynamic motion, including flipping, because we're having this fast impulse-like response. So I've shown you what happens if we work on just this sort of standard jitterbug formation, but what happens if we change the geometry even more? So this is what I've been telling you about of auxetics. So you have these rotating squares against each other, they hit this symmetric point, which is the point of greatest expansion, and then it collapses back down the other way. Instead of squares, we could imagine having rectangles instead. So as it moves through the motion, we don't just get equal expansion on either side. We have this sort of rectangular or shear pattern that comes up. We still get this point of symmetry, which is the point of maximum expansion, and then it collapses back down the other way. So on the mathematical side, one question that we might be interested in is what if we break this point of symmetry, and so that we get handed shearing auxetics instead? There's two ways to do this. One is we can make the unit cell be asymmetric. So now, instead of having two rectangles, we have one parallelogram. And so now if we go through the motion, yes, we hit this point of maximum expansion, but it's no longer symmetric, right? We no longer can achieve the opposite handedness of the other system. So this is what it would look like if we had mirrored it, but this new state that we achieve isn't the mirror copy of it. We have broken the symmetry of the system. The second way that we can get asymmetry is to take the rectangular shape, but instead put it off axis from the axis of symmetry. Right, so we have this cylinder and the expansion is still the same as what it was in the planar version, but now relative to the cylinder, it has this asymmetry associated with it. And this is the system that I'm going to be pursuing forward in the work. All right, so that was kind of a mathematical exercise of how we can break symmetry, but why do we care about this? We care about this because if we have one left-handed version and extend it, we can't change it into the right-handed version. So they're going to fight against each other and we can get a sort of a stable extension. So in this example, I'm going to show that we have left-handed and right-handed ones in this checkerboard formation so that we can make this robotic platform. And so we see from this that depending on which two that we actuate, we get a stable structure that can bend left, right, move up, down, and even twist in on itself. Right, here it is twisting in. And it's actually a pretty extensive range of motion. So it can go upwards by 60% of its original length, and it can bend either direction by over 90 degrees and do 3/4 of a rotation around. So this is a very simple way to get quite a large range of motion, all coming from the geometry. If we change the pattern even a little bit more, so in this case, we add this red constraint layer here, so that as the structure twists, it bends inwards rather than extending linearly upwards. We're excited by this because we can use this as the basis for fingers that kind of come in and clamp onwards. If we compare this to standard pneumatic soft grippers, we find that they're 20 times more energy efficient and are twice as fast at opening and closing. I ended up using this geometry design as the basis for a lot of different fingers. Since the properties were dependent on the geometry rather than the material, we could get new things like puncture resistance for recycling sorting. We could use the hollowness of the structure to put different suction cups on it, right? So this gripper combines the soft grasping with parallel jaw as well as suction, as you can see there. And then finally, because again, it's dependent on the geometry, not the material itself, we have a very soft gripper so that we can do things like safe grocery packing of fruits and vegetables. So I hope all of this kind of helps you understand more about where I'm coming from of using geometry as a way to get new material and robotic properties out of it. I'm going to now shift gears from actuation and motors to sensing, how we can use geometry to give us a sense of the world around us. This project was really motivated by plant structures. So if you remember from biology, there's xylem up and phloem down, right? Xylem is internal tubing inside the plant to take water up through, right? So here you can see the celery stalk in some water with blue food coloring. And if you were to cut open the celery, you now see that the blue food coloring goes through the structure. The xylem is moving fluids upwards through the system. So we're kind of inspired to do the same thing. So on the right, this is a 3D printed structure, but if you had X-ray vision, you would see these internal channels, these internal empty air channels inside. So the cool thing is that with these internal empty air channels, if we deform the structure, we will also deform the channels, and we can measure this deformation through pressure changes. So this is what the system looks like, right? We have the 3D printed structure. So in this case, this was the handed shearing auxetics I talked about earlier. And if you had X-ray vision, you would see these channels inside the overall structure. We connect these channels to tubing, and then we have these off-the-shelf pressure transducers. So something off the shelf that can measure the pressure of these internal air chambers. So by doing so, as the structure is moving around, we get a sense of what that deformation is. What's also important is we are 3D printing this structure, right? So it can be as complex as we want, and we can have these channels inside, and we have total design control of where we put the channels and what kind of geometry we put the channels in. So here we are, going back to the earlier cubic lattice that I showed you, and we put the sensors in this tic-tac-toe shape. So top, middle, bottom, left, middle, right. And then my co-author here is going to be moving the lattice into different like up, down, left, right movements. So you see, as we're doing this, we actually see the sensors reacting kind of how the deformation is going. So as we move from left to right, first the left sensors activate, then the right ones. We can also do very fast motions and we still get this behavior captured, right? So the signals are still very clean and we see distinct peaks for how we're moving it. In addition to deformation, in this example, we're going to move from left to right, pressing down on the system. And even then, right, like the left sensors react, then the middle ones, then the right. And we can do these very fast squeezes, and we still get this captured, even being able to tell things like, oh, the last one in the sequence was a harder press. So what's particularly exciting about this is because since it's based off of 3D printing, all of the sensing is internal to the system. So earlier when I talked about metamaterials being hard to have both actuation and sensing in a package, this method of fluidic innervation allows us to solve this. So here we have the same robotic platform for earlier that could move in these very large amounts, but we're able to collect sensor data here. I want to point out these are raw sensor inputs. When I first saw these, I thought these were actually the servo commands, but no, these are the sensor readings we're seeing. You can see in the middle and bottom ones, this orange, one of the sensors is not working as correctly, so we know that this is definitely the sensor data. Since we're relying on geometry, the system is extremely robust. We were able to collect 18 hours of data, which to my knowledge is the largest soft robotic data set, and the accuracy of the sensors meant we could estimate pose to within 8% of position and 7% of orientation. So armed with these two technologies, right, the actuation and the sensing, I'm now in my lab and my graduate students are exploring ways that we can combine these into a single system. A lot of the technology that I'm describing is built off of 3D printing. So we've been really interested in learning more about how 3D printing can enable this material intelligence. On one side, we had the motor abilities, right? 3D printing allowed us to make these unusual structures and almost have them come off the printer, just at electronics. 3D printing also enabled these sensory applications, right? By having these internal air channels, we could then understand things about how the structure was moving without having to do anything like add an additional component, right? We're getting closer to this big vision that we saw in the future of putting sensing, actuation, and computation all into the material itself. So now I'm going to be talking about new ways that my lab is going about. One way is through collaborations with the chemistry department to create new kinds of 3D printers. My chemistry collaborators, Dr. Zach Page at UT, has come up with this new hybrid resin. So if you shine UV light on the system, it has two, how do I explain this, like monomers in it, right? There's the yellow one and the gray one. And if you shine UV light onto it, only the gray monomers attach and you get a very soft structure. Whereas if you shine visible light onto it, both the gray and the yellow monomers react and you get this overall stiff structure, right? The yellow backbone is quite rigid. So this is very exciting because you now have this material that depending on what kind of light you shine on it, you either get soft or rigid materials. So here's what it looks like. It's like a picture of us doing both the softest version as well as the rigid version and some grayscale values in between. So by changing how much UV that we're putting onto the system, we can change how stiff or soft the system is. This is what the 3D printing pipeline looks like. So we have soft and stiff, this hand that's got internal bones inside. You can see the yellow bits here. And we send this to the 3D printer. It decides whether to shoot visible or UV light onto the system, and it projects it, and we get this new 3D printed structure here. This is what it looks like after it's all been printed. So you can see the yellow is stiff. It's hard to see the little bones inside, but we have this thing that bends accordingly, can do hook 'em. And we can get this kind of soft and rigid parts all printed out at the same time. We can now see single-shot printing of these complex robotic structures. So this is the bellows analog to that robotic platform that I showed earlier, right? This came just fully off the printer. So we could print the rigid barbs to interface the tubing onto, as well as the soft structures that can inflate and deflate at will. We're getting closer and closer to a robot that can just walk off of the printer. Another cool thing about having this soft, rigid printing control is that we can now add these new features and create new kinds of robots that would be almost impossible to make by traditional means. So in this case, we have two kinds of walkers. One is a simple case where we have rigid just for easier interfacing for the barbs, as well as this internal armor plate, because my student was having difficulty puncturing the structure to release the internal resin without damaging other structures. And so he's like, oh, that's easy. I'll just put this kind of rigid armor plate in here to protect it when I put the syringe into the robot. We also have this augmented walker here, which has a rigid fingernail. I think it should be a toenail, but a rigid toenail to push against the ground more easily, as well as these friction features, which are similar to cleats, right? They kind of help bite into the surface, but then as you move forward, they kind of fall away. So we get these complex features that at a resolution that would be very difficult to manufacture with traditional techniques. So here's what the robot looks like when we put it onto a surface. So you can see the little barbs here help it grip inwards and the toenails help it push back. So if we just use the simple soft walker, it doesn't move forward, it actually moves sideways. But with our new features like the toenails and the little cleats, we move forwards, still going sideways, but more forwards than before. We also have as reference this black line, which represents just a traditional printing a fully soft gripper with commercial technologies. And you might also notice that we only have one data point. That's because it bursts, right? It can't handle the pressures because it's not sort of it's only soft and it doesn't have this rigid combination to make it more robust to changes. Whereas we can actually, have a more robust grip, walker and go across the entire spectrum of surface grade. So from this, we are able to see how printing can start letting us achieve new kinds of actuations, new kinds of motors, and robot movement that we couldn't before. The other area that I'm interested in introducing is 3D printing for sensing. So using the technology that I've shown, but really focusing on the application space that it opens up. One example that I did during my postdoc was to collaborate with a lab at the NIH that makes exoskeletons for children with motor disabilities. So here you can see that there's a child who is using an exoskeleton to exercise, right? To sort of train them to use muscles that they might not originally use. This is what the exoskeleton looks like off of the child. There's not a lot of space to work with. In fact, all of these holes that are cut out, they're not just for weight. They all have some clinical feature. So to put like surface electrodes to measure the motor activity, or easier ways to measure joints and torques. So since there's not a lot of real estate, where can we add sensing to it? And what I proposed was to look at these sensorized straps, or to sensorize the straps. If you've ever worn a leg brace, you know that there's just these pads there to help cinch it to your body and give you a little bit more comfort. But on a clinical sense, these pads aren't doing anything. They're just, padding. So the thing that I proposed was to use the 3D printed sensors that I made, the fluidic innervation, and use these to make sensorized pads to provide some force information for how the person is moving. In preliminary studies that we saw, so this is a machine called a dynamometer, which measures human torques. So the person is going to kick outwards, and we can measure the torques they're exerting. But we also include the new sensors that we've made to get a force reading that way as well. This is all very preliminary results, but we still see that it's a very high correlation, right? The blue is the ground truth, the dynamometer machine that is the gold standard for measuring human torques. And in orange, this is what our pads are measuring. We saw an R-squared value of about 0.9 for the thigh pad, and we saw a lower one for this shank pad, which we're pretty sure is because of this other pad that we have here. So it's preliminary results, but we're very excited about how it's shaping up. As I showed earlier, we're also putting these pads onto children who have motor disabilities. And again, very preliminary results, but this is the ground truth for a person's muscle activity. And this is the measurement that we're reading from our pressure pads. So we're seeing a correlation between these two results, and we're looking into it more to see if we can give more explanation, like a biological explanation of what these pads are measuring. The other case where I'm starting to use these tactile sensors is in grippers for new kind of human-like reflexes. So in this video, you can kind of see how we fabricate it, right? We 3D print it with these empty air channels inside. I will go backwards, right? We 3D print it with these empty air channels inside, which we then clear out with solvent. We cure them. We add these pressure transducers to connect to the overall structure. And we can, again, since it's 3D printed, we can do it for any kind of gripper of interest. The way that we're using these pressure sensors is similar to how you have sensing underneath your skin. So just like you have these different kinds of mechanoreceptors to measure pressure and frequency, so too do we have it here. So here's the gripping surface, and we have a pair of sensors from the front and the back. We are measuring the difference between these two pressure sources so that we can get the signal that gives a sense of the deformation of the structure. What's very cool about this is we have shown earlier that we can measure forces, but we're also able to measure vibrations using this technique. So when you pick up an object, you're actually constantly adjusting how you're grabbing it. So if an object is slipping out of the grasp, you're tightening your grip without even thinking about it. So here's maybe some of the cases where slip occurs. It's very hard to see the difference between these two pictures. That's because it's a tilt change of about 1.5 degrees and it's shifting by 1 millimeter. Same thing for this glass as it drops down. And indeed, if we look at the pure pressure readings of the sensors, they look very flat, like almost like nothing has occurred. But by doing our favorite frequency sampling techniques like Fourier transform and power spectral density, we can start to tease out some features that occur in here, resulting in a very clean signal to tell when slip is happening or not. So what this means is that we now have this gripper that can measure force and act accordingly, right? So here's a potato chip getting harmed, right? So if you don't have this force sensing, you're not able to measure the force which you're grasping it, and you just crush it, right? With our system, we're able to measure forces to within 0.1 newtons. So we can say, oh, we're starting to apply too much force, we should stop and then lift up the chip. This one is an even cooler example where we're combining force and slip together. So we're going to pick up these glasses, right? And we're going to exert just enough force so that the legs don't move in, but also detect slip so that we can adjust our grasp accordingly. So here we're picking up the gripper, we're picking up the glasses. The glasses slip and we catch it, right? Kind of similar to how humans have these reflexes and are able to act accordingly. We're sampling the sensors at 2 kilohertz, so we can detect a slip event within 100 milliseconds. So I hope that I've given you a sense of how we thinking about materials and geometry can really get us to this almost reflex-like abilities in robots. I've talked to you about how geometry affects movement and actuation. I've talked about how we can use geometry to think about new forms of sensing, and I've shown how we're starting to put all of these things together by considering the ways that we 3D print and make new actuators, as well as ways that we can use it for sensing in both medical devices and robot manipulation. So with that, I'd like to thank all of my collaborators, with a special shout out to this box in red, which are grad students and undergrads I mentored at MIT, and this box, which is grad students and undergrads I mentored at UT. So very excited for this slide to get even more busy and more cluttered with folks. And with that, I'm happy to take any questions y'all have.
Yeah, go ahead. You hear me okay?
Yeah.
I just wanted to know, for like all of your robots, for all these like sensing experiments, is it like, I guess since like we're like an AI club, is it like manually programmed or like do you like train a model to like detect these like really small, I guess events per se? I don't know
Yeah.
the right way to word it.
No, no, no. Let me see. Let's look at all the robots. So my background is in electrical engineering and computer science. That's what my degree is in. But as you can see, I'm like pretty hard on the mechanical side as well. So for all of this stuff, these were all just like pretty simple controls, like using a servo, right, which has some feedback in there, and then just telling it to like move to a specific position. For this one, oh, I think I have a backup slide actually. Yeah, here we go. For this one, where we're predicting where the robot platform should go, we fed it 18 hours of data, and we just used a 3-layer LSTM in order to say, like, here's the time series data. Can you predict the next pose for it? And then finally, I had some programs that some papers I didn't discuss, but you can see this is like a Tisney plot, which is just like a simple machine learning clustering algorithm. And it's, again, very simple neural network, one hidden layer, 256 neurons, right? Like less than 2 seconds of training in order to get this information out. So I think that's like a good point, is that if you're using the geometry and like making a clean hardware signal, your computation becomes much easier. So I think the final thing is this one. Do I have the force? I don't. I might have the force data. Give me a second. Okay, I don't have the force information for this. But the way that we predicted force for this one, it was like a linear regression, I think. We just collected a couple of datas. And then this is purely analytical of doing like Fourier transform, power spectral density. So kind of a mix of learning and analytical techniques. Yeah.
Thank you.
I had a question about the fluidic innervation. So, right,
Mhm.
examples that you showed are pretty small, like with the rippers and the walker and whatnot.
Mhm.
But future, if you were to scale it up to something for like humanoid applications, how would you go about like making these sensors bigger?
Yeah. So the biggest challenge actually is making it smaller. Because the big limitation is that have you done resin printing before or
I'm familiar with it, but I haven't. I'm more like an FDM person, so.
sure. Okay, so what's a good okay. So for folks who aren't aware, resin printing is like instead of having like a nozzle with melted plastic that comes out, you've got this vat of goop, and then you are like curing one layer at a time through like UV or something, and it comes out of the goop. But the problem is that the goop is very sticky and it like clogs things. So the main challenge is making sure that this is clear, because it's going to be full of goop normally. That's also why in where is that image? In this one, right? So this is like fresh out of the goop. You can see it's sticky, right? And we're doing this like air channel cleaning process. So we have this squirt bottle and we're like literally trying to clear out the channels of stuff. So if it's larger, it's actually easier because we can do things of like taking a rod and like reaming it out, or like we can mechanically do it rather than just relying on chemical stuff. So I actually recently got a grant working with Toyota Research Institute to explore exactly what you're saying. All right, there's like all these big like panels of humanoids that aren't being like useful. They're just protecting electronics. So hopefully we can put the sensors straight in there.
I had a question about the prospect of like doing this printing, but doing it for more features, like you said, conductivity, rather than just like changing the structure of it. Is there any hope of being able to do that sort of really fine-tune printing?
Yeah. Um, so I actually have I'm in an ECE department, so even though it looks very mechanical, all of my students are a computational side. So on the one thing is like all of this like fancy geometry, this was me back in undergrad just like manually trying stuff out. But now I have one student who is doing the math like, you know, actually changing like sorry, this is all just geometry, right? So you could imagine changing, like creating different patterns by saying, oh, what's the length here? What's the width here? And like, let's just like put that on a slider and change it. So I have one student who's doing that so that once it's parameterized in that way, you could imagine exploring the design space, right? Like writing some graph search algorithm to just like explore all of the different geometries and seeing what results comes out from here. I also have a student who's making soft body simulation so that, computationally designing the system is one question, but then like how is it actually going to perform? And they're making the simulator for that. So hopefully instead of manually just trying a whole bunch of different things, we can say, hey, we want these material properties, and the neural network or whatever design algorithm we have spits it out for us. Yeah.
Um, I was just gonna ask, so yeah, you come from a electrical engineering and computer science background, and like you're much more on the uh, chemical, mechanical engineering side of things now. So I just wanted to ask regarding like the career trajectory, like how did you decide or how did you pivot in that direction?
Okay. Let me pull up slides from a different talk. I think this one. Okay. Let's see. Okay. So how did I get into robotics? I was very lucky that in high school I was doing FRC, like first robotics. And I was captain of the coding team in high school. So that when I went to college, I was like, okay, I've done this robot thing, like I'm gonna try something new. And I like tried to do everything that wasn't robots. So I had a software engineering internship. I worked on embedded systems. I did glass blowing because we had a class for that. That was pretty cool. That's how I got into mechanical engineering. Like I came into college with like a mostly coding background, but by doing more and more hands-on stuff, I was like, like mechanical engineering is like the fun part because I get to build stuff. I loved my Coursera internship, but it was all just website development, and I was like, I needed something tactile. And so through that, I got to learn machining and building stuff. But at the same time, I was doing a lot of side projects that still kind of looked like robotics. But for me, it was just like hanging out with friends, right? So we made a guitar playing robot. There was like a 1 month long competition on like robotics. And I was mostly on the coding side, I think, for this one. And then also I was doing a senior capstone course that, it has the embedded systems part into it. But all of these things still had robotic elements in it. It's a combination of mechanical and the computer science things. So when I got into, or I guess this was my senior year, I got into robotics research, where they presented this like handed shearing auxetics idea to me, and they're like, make this work. And my pictures are all just of failures, actually. Like you guys got to see the very polished version, but during undergrad, like I'm causing fires on the laser cutter. Like things aren't working. You can see my notes for it. And like even this, like this was the picture that I had of it's not motorized, right? Like I'm turning this thing with my hands. So there was just something about it, like being in robotics and being able to be on this bridge between mechanical and electrical, that even though I was having a lot of difficulties with it, I still wanted to keep up with it. So I've always been kind of doing this like weird path in the middle. Uh, so if you're interested in this kind of things, I guess my best advice is like one, try a bunch of things, see what you like, right? If the mechanical stuff's interesting for you, there's definitely people who are exploring it, right? Like my lab is one, and I think Ankur Mehta, in the EE department at UCLA is another person. But yeah, just it's a lot of work. It's a lot of work to do both, but just try and explore as much as you can. Yeah.
Oh, also, if you guys have any questions regarding like grad school applications, PhD, master's degree, etc. I said that in the Discord, right? So if you guys are interested in that direction, like feel free to ask those questions also.
Um, I guess I have a question about the research, but it's not like very technical. It's kind of just like, for example, you said you had, or I don't know if it was you specifically, but like your lab had the idea of putting the sensors on the pads. Like, is that like a very formalized process, like for proposing an idea like that? Or is it kind of just like someone says during a lab meeting, like, hey, let's do this, so that everyone just does it? Like, it doesn't feel like scientifically derived from anything in particular. Obviously, it's like a good idea, but like, I'm just wondering, how that ends up happening.
Yeah.
Right.
Um, yeah. Is this sharing the original presentation or the old one? Me.
This is showing the second PowerPoint presentation now.
Okay, let me reshare. Let me reshare this. Oh, let's see. Okay. I'll do okay. So I really want to write like an oral history, I guess, of how these projects go, because like for this auxetics, right? So what you guys saw, this is the very polished talk. This is like the talk that I give when I'm like giving talks at other universities. But like, how did this project start? Like, I was an undergrad, and then Jeff was like, "Hey, like, actually, I want to share the other. Let me just share screen. I think that'll be easier. Screen. Okay, Jeff, this guy, right? He's like, I made this, make it into cylinders. And I was like, okay, like I'm an undergrad and I don't know what I'm doing, right? And so that's why like stuff's on fire. I actually got very sick from this, because I was laser cutting Teflon, and the FL in Teflon stands for fluorine. So I got Teflon flu. Like I'm still kind of a little upset he didn't tell me that like there was a safety risk of it, right? But like if you're saying like scientific process, I was literally an undergrad and it was like, go do this. And I was like, you got it. And then over time, like you start working on projects, and then I worked on this one, and we're like, okay, more of a story is starting to develop to the point where, like, when I'm talking to you guys, I have this very fancy story about like reflexes and whatever, right? But that's not really like how it came about. How it came about was like one thing after another. And so the story behind, where's one? This one, this thing is I got a fancy postdoc where they paid me a lot of money to be like, okay, whatever your PhD research was, do something completely different. So I went to the NIH lab to Tom and I was like, hey, I have these sensors. Uh, I know they're cutting edge for robotics, so that I know they're 100% going to be cutting edge for whatever you're doing. And it took a lot of like discussion of like, oh, like he's like, I guess I work on exoskeletons and we care about forces. And I had to come up with the idea of like, oh, maybe these braces would be like of interest. But that's kind of like um nothing is really clean, right? You go to these talks and they give you a very clean story, but when you're actually doing it, it's very messy. You just talk to a guy. Okay, maybe one more story time, and that's it. Okay, so out of this, right, this guy is the chemistry man who like has this sensors, and then this student was interested in working with me, right? And this student had a lot of experience in chemistry, and I was like, I don't do any chemistry. Like, you'd have to be co-advised if you want to work with me. And he's like, okay, what about this guy? And then I talked to this guy, Zach, and Zach says, I've made this resin. I have no idea what to do with it. And I'm like, what do you mean you have no idea what to do with it, right? Because like I'm in soft robotics, and this is almost like the holy grail for soft robots to make something soft and rigid and connected together. But like if I never talked to that guy in chemistry, he'd just be like, like it seems cool. We'll just like derp around and like come up with some stuff, but he'll never come up with those robotic applications. So yeah, that's about all the advice I can give you. It's really not as clean if you keep going to these talks. It's very, very messy process.
Do you think this is unique to like the research you do, or it's just true of like academia in general?
I think this is true of academia in general. I think it's even more true for machine learning, since this is an AI club, right? It's like,
We tried and it works. So we'll publish it. It's so
right, like if you look at the transformer architecture, there's nothing like unique about it. It's just kind of like you've stuck their linear algebra in different ways. And it just so happened that this way to stick linear algebra like is very parallelizable. It's like amenable to GPUs, so you can just make these huge systems, right? But I think it's like, yeah, I have a lot of stories, including one of like a guy doesn't do his dishes and then he gets his PhD done in 2 years. Yeah.
Nice, very, very nice talk. I noticed on your final slide, you had, NSF and Hertz fellowships, right?
Hmm.
Or, yeah, did you have the Hertz fellowship during,
Yeah, I did. Yeah.
I was wondering, so I, I didn't apply for Hertz this year. I was wondering, in general, for like fellowship applications, do you have any advice on like, for like research proposals and that kind of stuff?
Um, I think probably my best advice is to be working with the professor so they can help you with the story, right? So what I was talking about earlier of like in the weeds, it was literally like Jeff being like, do this. And I was like, yes, right. But coming up with this story, like this whole reflex things and like, how robots fit in the world, this is like what a professor is good at. So your research statement, especially for Soros, is different, but like Hertz doesn't really have a research statement, especially for the NSF. Like it's kind of rough because I think they do kind of assume that you're working with a professor who can give you that story. Um, so I think that's the best advice that I have for those. These are a little weird. Um, I don't know what Hertz is looking for, I would say. The most famous thing is that they ask you a lot of like Fermi estimation questions, right? And you're kind of like thinking on your feet, but I don't really know like what's a one criteria they're looking for. Whereas the Paul and Daisy Soros, they like really care about immigrant It's like excellence. They're almost kind of like weird about it. So yeah, I don't really know. But I think, even if you think it's a long shot, it's still worth doing it because this kind of like storytelling, contextualizing your research, communicating, this is as important in grad school as the actual technical part. Like you guys saw how I like had this story and it like sounded very convincing, right? I'm not lying at any point in the stage, but like it makes it a lot more compelling and people are interested in hearing more than just being like paper one, paper two, and we're stapling it together. Yeah.
Yeah. How did you win College Jeopardy? Oh yeah,
Uh,
doing that in like the Discord. I was like, oh yeah, she won the College Jeopardy.
yeah. So one, you can just try out. Like, if you guys are interested in trivia, there you can go. I can just even pull this up right now of like, uh, so there's like a test that you could just take online. Oh God. Right. You literally just take the test, like anytime, take 15 minutes, like do the test. So I got into it because my RA was on Jeopardy and we were all just like, yeah, like cheering Phil on. And then the next year Phil was like, hey, at that time you couldn't do it anytime. There was like set times you could take the test. And he was like, you guys should try it. So I I tried it my first time. I got invited to the second round where you had to go like in person to New York to like try out, and I didn't make it past that one. So then I tried it again the following year, and I went to New York, and I was like, I'll just take a trip to New York. It's not gonna do anything, and then I ended up going on the show. Now since it's post-pandemic, it's a lot easier. You can take the test anytime, and they'll do a Zoom interview if you get to the next round. But then it's like, yeah, you just go on there.
Thank you.
Yeah.
Yeah. Well, being yeah, guys, I'm being touched on this. Yeah, it's good. Well, thank you so much, Lily. Thank you so much for giving your time out of your busy day. It's like UT's having a football game right now.
Yeah, we're winning, so it's okay.
Okay, yeah, but it's been a great talk. It's been really great to get on a Zoom call with you too.
Yeah.
Yeah.
Please, you Austin. Yes. What about Arch Manning?
Oh, it's that guy.
That is that guy.
Oh, I don't know this. Okay, yeah, but thank you so much for your time.
Yeah. Thanks for inviting me. All right. See ya.
I guess, I guess you